All right. Yeah. YouTube videos, yeah. All right, so our evaporation assignment is going to be due a week from today. That gives us a little bit more time to look at some examples today and a couple more examples in class on Tuesday. I've handed out an equation packet that you're going to be allowed to use on the day of the exam, along with one page of your own notes. Front side only, but you can put whatever you'd like on it. You can put on other equations that you don't find in the packet. You could put in definitions of words. You could put in problem-solving procedures, positive affirmations, whatever you'd like to have the day of the exam. The equation pack that I've just given you is, as you might guess, it's the FE manual, but it's the revised 9th edition that just came out. The computer-based test starts in January, and along with that, they've revised the FE manual, and it's available as a download online. You can go to the NCEES website and download it. It's free. But there's the hydrology section. That's what they provide to you. And I'll do my best along the way for our final particularly to give you questions that will allow you to actually use the manual as it's written there. So one of the challenging things when it comes to hydrology is that every book has different units, and even the federal government can't seem to get symbols unified. You know, the Department of Agriculture may use one symbol for different formulas, and the even within the Department of Agriculture, different offices may be using different symbols for different variables. The Army Corps has different terminology, so you just sort of have to get accustomed to the equations as they're written in the packet there. So any questions on these announcements or schedule items for upcoming classes? No, just the front. Mm-hmm. Okay, well, today we're going to take a look at some applied problem solving having to do with evaporation. In class last time we were looking at one of the two factors that, depending on the way you look at it, either drives evaporation or limits it. And so broadly speaking, last time in class what we were discussing is how solar radiation drives the evaporation of water. If we have a pan of water and the sunshine is going down, it is the radiation that is heating up the water and causing as the water heats, there's molecules of water, and when there's enough sequential collisions of molecules in the liquid phase that there's quite a bit of kinetic energy for one of the molecules, then it will escape through the liquid-air barrier and become vaporized. Not all of the liquid particles will have enough kinetic energy to go into the vapor phase, and that's why evaporation rate's a function of temperature, is that the higher the temperature, the faster the kinetic energy of the water, and the more quickly the latent heat of vaporization can be provided to water for it to evaporate. So here we're going to work an example of a lagoon that happens to be located close to Dubai. It's called Khalid Lagoon. And we have a measurement of the incident radiation in the area. And this would be data that's collected from a device called a radiometer. It just measures the light intensity at a certain time. And at noon on February 12th, the incident radiation is 978 watts per square meter. This is similar to data that you can look up online. And in fact, the data that you are assigned to look up for the homework project is going to have similar units of watts per square meter. In this case, we know the water temperature is 26 Celsius, air temperature 28.5 Celsius, relative humidity is given, wind speed is defined. Now, we don't yet use wind speed when we're just considering the energy method. There are basically two limiting factors. There's the energy being delivered to the water, and then there's also the limiting factor of the wind over the surface of the water. And what the wind is able to do is it's able to transport moist air away from the water surface, and simultaneously it's bringing dry air over the water surface so that it can evaporate even more. Evaporation is really slowed down when you have completely saturated air over the water surface, because if the air isn't able to absorb any more moisture, it doesn't matter how much solar radiation is being delivered. You can have plenty of heat source, but if there's no capacity for the air to absorb any more moisture, then evaporation will cease. In this example, although we know some information that's characterizing wind speed, we're just going to be focusing on the energy side of this problem, of taking a look at how quickly energy is delivered to the water. So we've got an equation for the latent heat of vaporization. It's how much energy is required to vaporize water as a function of temperature. It varies. We know the relationship between the radiation, the net radiation, which is the difference between emitted radiation and reflected radiation. And in the case of sunshine coming in like this, there's going to be a certain amount of radiation that's just reflected off of the surface. And also, the water itself has the potential to be radiating in addition to that, which is reflected off the surface of the, so radiated heat. And that's what's accounted for here. R sub E is the emitted radiation. That's just a function of the water temperature, as you can see. This term 1 minus alpha takes into account the reflectivity of the surface, where alpha is called albedo. And we're going to assume that the albedo of the surface is 0.35. And so between accounting for the emitted radiation and the reflected radiation, we'll have this net radiation. And in the energy method, you assume that the evaporation rate is simply, if there's no other limiting factors, how quickly you evaporate water is how quickly energy is delivered, and then it's also a function of the latent heat of vaporization, and then for units purposes, we take into account the density of water. And so let's work through this example together. All right, we've got that the albedo is 0.35. The emissivity of water, this is a constant that we can look up. It's called the radiation emissivity of water. The Stefan-Boltzmann constant is 5.67 times 10 to the minus 8 watts per meter squared times Kelvin to the 4th. And that's another constant that's worked into most of the methods for estimating evaporation. The water temperature that we're going to work with in this example is 26 degrees Celsius, and we need it to be in Kelvin. And so we can convert that over, and it's 299.15 Kelvin. And with that, we can find the amount of radiation that's emitted. And that's a function of the radiation emissivity of water, the Stefan-Boltzmann constant, and the temperature of the water. So we substitute in the known constants. And the known temperature. And we have that the radiation emitted is 451.8 watts per meter squared. And that means for every square meter of area, the water is emitting 451 watts per square meter into the air. Now, you'd be right in wondering if the radiation emitted by the water isn't somewhat affected by the temperature of the air. But you can see that all this formula is taking into account is the temperature of the water itself. And so it stands to reason that if the water was very warm and the air was very cold, then of course the water would be emitting more radiation than otherwise. But this formula doesn't take that into account. This is an empirical equation, this formula for R sub E. That's not a immutable physical relationship that is defined really by that expression, but rather it's just an estimation of how you can calculate the radiation that's emitted. There are other equations that are more sophisticated and complex and frankly would do a better job, but this is a sort of quick and easy way of estimating how much radiation is emitted by the water surface. So without taking into account the air temperature quite yet, this is a way that we can estimate how much radiation the water itself is giving off. What we want to calculate now is the net radiation available to drive evaporation. Okay. The incident radiation, R sub I, is the 978 watts per square meter. So the net radiation, this is the difference between how much has been received by the surface minus what was reflected out minus what is being emitted by the surface. And so this is the leftover energy. There's 183.9 watts per square meter it's an instantaneous measurement right at noon. This is how much energy is available to drive evaporation. It's the energy that wasn't reflected and wasn't emitted by the water itself. So this is the energy that can actually speed up the molecules, give them the kinetic energy they need to overcome the phase change from the liquid phase to the vapor phase. And so if we put this into the the formula for E sub R, we're going to need to know what is the latent heat of vaporization at the temperature in question. The latent heat of vaporization is 2.501 times 10 to the 6th minus 2370 times T. Okay, that is and the thing here is that the air temperature, when it goes into the latent heat of vaporization, that T actually needs to be Celsius. So it is the air temperature in Celsius for this formula. Okay, so that is if you're keeping track of the units, a joule per kilogram would be the same as a watt second per kilogram. Okay. Let's put it now into the equation for the evaporation rate, E sub R. we get that the evaporation rate is 7.58 times 10 to the minus 8 meters per second. So that's a pretty small quantity. If we multiply it by 86,400 seconds per day and multiply it by 1,000 millimeters per meter, then that gives us an evaporation rate of 6.55 millimeters per day. What we learned in the last class period, that was over the average of the Earth's surface, it's about 3 millimeters per day of evapotranspiration. And so this is in the realm of possibility. This seems somewhat reasonable that in open water it would be higher than the aerial average, and this is during the winter time, but fairly near the equator on sort of an average day. Now, the other thing that we have to keep in mind is that this radiation measurement was at noon, and so we're extrapolating the evaporation rate at noon over the entire day. And obviously, you're not going to have the same radiation at noon as you are at midnight. And so for us to be a little bit more accurate in converting this instantaneous evaporation rate into a daily evaporation rate, what we'd probably want to do is multiply that, instead of by 86,400 seconds per day, maybe what we'd want to do is multiply it by the number of seconds of daylight per day. So that's not a measurement we have in this description, but this is the instantaneous evaporation rate in terms of millimeters per day at noon. Any questions so far when it comes to the energy part of the evaporation method? It characterizes the reflectivity of a surface. And so what it means is that of the radiation that comes down into the water, 35% we're assuming is reflected. And so 65% of the radiation actually is absorbed by the water.
So relative humidity and wind speed don't have anything to do with this calculation?
Not yet. This is just the energy side of it. But, I mean, it obviously is important. And so the other part of evaporation is called the aerodynamic method. We've been looking at the energy method. The aerodynamic method says, well, it's not just about how much energy is being delivered to the water, but it's also about how quickly the moisture can be wicked away from the water surface, because evaporation is going to be limited if there's 100% humidity in the air. And when you have transport, which is being illustrated here, is consider a control volume over the surface of the water, where at the bottom of the control volume you've got just a little bit of water and it's evaporating. You've got moisture inside of the control volume, and how quickly the water vapor can be transported away dictates how quickly the evaporation will actually occur. And so in this previous example, what we were saying is assume unlimited transport. The only limiting factor here is energy, in the energy part of the equation. It's flipped in the aerodynamic method. The aerodynamic method says, let's assume unlimited energy and instead just concern ourselves with how quickly the moisture can be moved out of the area so that more evaporation can occur. It's sort of like a traffic jam. You can only have one car come into the freeway when one car comes off the freeway, when it's completely crowded. And if you've got completely saturated air, there can only be another molecule of water joining the vapor phase when a molecule of water is transported away. So the driving force is the difference between how much water is in the air and how much water could be in the air. And in that case, if you have more wind, then that increases the rate of transport and therefore will increase the rate of evaporation. Here's a diagram that shows what you'd expect is at the surface of the water, the velocity is equal to 0. And this may take your mind back to the beginning days of fluid mechanics when we described the no-slip condition. And the no-slip condition, when we would draw a velocity profile in a pipe, what we'd have is that bullet shape. where we'd say that at the center of the pipe the velocity is high, but then at the edges of the pipe the water velocity is very low. And in fact, right at the border between the pipe and the water is stuck. It has no velocity. There's a boundary layer of water that's stagnant and not moving because the shear forces of the pipe are pressing on the water and holding it stationary. And the same thing is true here. If you have wind flowing through that control volume, the wind at the bottom of the surface has no velocity. And so the air is, the water moisture is going to be, the moisture that's in the air is going to be transported away from the surface by diffusion because it can't be advection. The velocity of the air is zero down at the surface. And the other thing that this figure is depicting is that the temperature of the air is decreasing as you go up. And that's, as you remember from our discussions about how rain occurs, there's the adiabatic lapse rate that says that as you go up through the atmosphere, pressure is decreasing and therefore temperature is decreasing. And so we have both of these things happening simultaneously. Low velocity at the surface, increasing velocity aloft, and so it's easier for transport to occur further away from the surface, but the temperature is lower up aloft. And because of that, the humidity is high at the water surface, and the humidity is decreasing as you go up because there's more transport up there, and also the temperature is lower. Here are the equations that are associated with the aerodynamic method. Some of the things that we're going to be concerning ourselves with are the saturation vapor pressure versus the ambient vapor pressure. And these are both measurements of how much moisture could be in the air versus is in the air at a certain condition. And the vapor transfer coefficient is a constant that relates, if you know the difference between essentially humidity and how much moisture could be in the air, then you can estimate the evaporation rate. For us to calculate that constant B, we have to know what is the wind speed. So U is a function of wind speed, and it's measured not at the surface, because remember, at the surface the wind speed is zero. And so the velocity of the wind is measured some distance up off the water surface. And Z2 versus Z0 are measurements of both the height at which the wind velocity was measured, and then also the roughness of the surface. So if there's lots of choppy waves, then Z0 would be larger, but if it's really smooth conditions, meaning the water surface is glassy, then Z0 would be lower. We estimate the saturation vapor pressure according to this expression, and this is another one that's just an empirical equation. All of these are just empirical equations that are estimating things and aren't the sole definition of how you actually characterize the, in this case, saturation vapor pressure. There are other equations that are more accurate than this, but they're more challenging to solve and require a greater number of inputs. And so this is an easy simplification, and it relies on the air temperature to find what is the saturation vapor pressure. If it's fully saturated with moisture, what would be the vapor pressure of liquid in the air? And then we measure the ambient vapor pressure as a function of relative humidity. So it's the same problem description here. We have this lagoon near Dubai, and we have the same radiation. In this case, it's the radiation that we're not going to use in the calculations, because the aerodynamic method assumes we've got plenty of radiation, but what really counts is how quickly you can move the moisture away from the water surface. But in this case, we are going to start using, for example, the relative humidity of the air. We're going to use the wind speed. And now we're also going to take into account the roughness of the water surface. So the average wave height here is 0.03 centimeters. So 0.3 millimeters is the average wave height. And that's probably a pretty calm day if you think about it. We'd see waves larger than that fairly often. So let's try applying the aerodynamic method here. Whose umbrella is that? That's cute. It's very nice. Aerodynamic method. The first thing is we're going to calculate, or rather estimate, E sub AS. That's 611. And EXP, of course, means E to the power of. So EXP 17.27 times 28.5, which is the temperature, 237.3 plus 28.5. $38.93 Pascal. Now we want to find E sub A, which is the ambient conditions, and we're assuming that it's a function of the relative humidity. E sub AS times the relative humidity. So that's 38.93 pascals times 55% relative humidity. So 2141 pascals. And we've got that the wind speed is 2.7 meters per second, and that is measured at an elevation of 2 meters above the water surface, and the average wave height is 0.03 centimeters. Okay, so now we have all that defined. We can measure B, 0.102 times the quantity U2, and then we're going to have the logarithm of Z2 divided by Z naught, and that all will be squared. Okay, so 0.102 times 2.7 meters per second, and the logarithm of 200. We have to have units consistency in Z2 and Z naught. If we're going to have centimeters for Z naught, then we have to have centimeters for Z2. So Z2 is 200 centimeters divided by 0.03 centimeters, which was the average wave height. Square that. 0.0036 millimeters per day times Pascal. And therefore, the evaporation according to the aerodynamic method is going to be B times E sub AS minus E sub A. And so the B is estimated by us as 0.0036 millimeters per day per Pascal. And then the E sub AS is 38.93 pascals minus 2141 pascals. So if we put everything together, then we're going to get that it's 6.31 millimeters per day. And that is assuming unlimited radiation and that the rate of evaporation is governed strictly by transport. Okay. Can there be evaporation at night? Is it possible for water to evaporate at night? Yeah, from the long wave radiation. It can evaporate, and it gets the energy from the ground emitting the energy. And so we know that evaporation has to have an energy source, and it has to have transport. So yes, there can be evaporation at night as long as there is something supplying the energy for the evaporation to occur. And so it may be in a lake, for example, that the water underneath the surface is warmer than the water at the surface. And it's it's typical for as the air cools, then the water that's in contact with the air will cool a little bit, but underneath the water surface it will remain warmer. And you see that in the wintertime when the surface of the lake freezes, but the water underneath that ice layer doesn't freeze. That's how fish live through the winter, is they're swimming around in the warmer water that's down beneath. Since water is most dense at 4 degrees Celsius, then it's actually at the winter time, the warm water at the bottom of the lake, and it gets cooler as you move towards the surface and have 0-degree water in contact with the ice. In this case, though, assuming unlimited transport on a daily basis, no, unlimited energy, then just the wind profile and the humidity conditions are such that we could get 6.31 millimeters per day evaporated from the lagoon. So on the one hand, we assumed limited energy, but unlimited transport. So here, this guess was limited energy, unlimited transport. Whereas the aerodynamic method said we have limited transport and unlimited energy. So what would be a way for us to get a better estimate than either of these two methods? Put them together, combine them. Now remember that in addition to the fact that we were assuming unlimited transport here, when we came up with our daily estimate, that was also assuming that it was sunny all day long, 24 hours a day. That's not true. We didn't have that same weakness over here. It very well could be 2.7 meter per hour winds all day long. That's a stiff wind, and that's it's not like a hurricane or anything, but you know, that's pretty windy. But sure, maybe it's windy day and night, but it's not sunny day and night, right? Not at the equator. All right, so we're going to come up with a combined method, and in the combined method it says, well, we're not going to assume that there's unlimited energy, and we're not going to assume there's unlimited transport, and so let's put them together somehow. And what's represented on screen here is one of the many, many, many ways of averaging the two approaches. And the method that's used here is to calculate the gradient of the saturated vapor pressure curve and what's called a psychometric constant. And both of these terms are actually used in other methods as well. The Penman method is what's most commonly used in really sophisticated calculations of evaporation. This is a little bit of a simplification of what the full combined approach is. But we can use it to come up with a better estimate of the evaporation. You can see that it's basically you're weighting the two. You're saying that the overall actual evaporation is sort of a weighted average of how much the radiation limited evaporation was, and here the transport limited by the aerodynamic method. You're averaging the two together. Priestley-Taylor approach says, well, rather than calculating both the aerodynamic and the energy method, let's just say that it's 1.3 times the averaging factor, and then it's really a function of the energy limiting more times than the aerodynamic limits. So let's continue this example here, and what I'd like you to do is calculate this according to both the combined method and then also with the Priestley-Taylor method. And the thing that you need to know about calculating the sigma is that the temperature you put in here, the temperature alpha, this should be the 28.5 air temperature. So temperature alpha, that's air temperature in Celsius in order to calculate the term delta. All right, so in the combined method, what we do is first of all calculate delta as a function of the temperature of the air and E sub AS. It's 225.8 pascals per degree Celsius. We know that gamma is 66.8 pascals per degree Celsius, and so with that we can calculate the combined method evaporation rate is this weighted average of both the energy method and their aerodynamic method values that we calculated earlier, and we come up with the combined method is predicting 6.54 millimeters per day. Now before we just accept this as a good solid estimate, remember what was the huge weakness of what we did in the energy method? When we came up with this 6.6 millimeters per day, it was based on what? What's that? Essentially, because we had a measurement of the net radiation of 185 watts per square meter at noon. So what we did is we assumed basically that radiation value would be there all day long, you know, from midnight to midnight. And so this 6.6 millimeters per day was just, we took one instantaneous measurement of radiation intensity and we extrapolated it over the whole day. What's better to do is have an hour-by-hour measurement of solar radiation. That's what you're going to do in the homework. You're going to take this combined method and you're going to estimate what is the evaporation rate at every hour, because that's what we have the measurement of radiation intensity for. And so you don't have to go through and do it on paper every hour 24 times. Obviously, you set it up once in the spreadsheet. You have the radiation values as a column, then you can calculate the evaporation rate as another column. And so we would have had different combined method, because the true value of instead of 6.6 millimeters per day, it's probably a lot lower than that, since it's not going to be sunny all 24 hours a day. But you can get a sense for how the combined method averages it together, and according to this example, we get 6.54 millimeters per day when we calculate it by the combined method, or if we just use the Priestley-Taylor method, the assumption being 1.3 times the energy part of the combined method, then you get 6.62 millimeters per day. And so it's a pretty close estimate, and it saves us the trouble of having to go and calculate the aerodynamic aspect of the combined method. Any questions? That's a constant. According to, well, we're assuming it's a constant. It's not really a constant, but we're assuming it is. It varies as a function of elevation. In the big fatty spreadsheet that I made for the DEP, let me see if I can find how I had calculated gamma in that. Where was that? Yeah, there it is. So there, no, I was assuming, I kept it as a constant as well, a psychometric constant. But I calculated it based on something that's called lambda, the latent heat of vaporization. It's a function of the latent heat of vaporization and also the atmospheric pressure. So in reality, well, we're assuming it's a constant, but it changes with temperature and atmospheric pressure. But it doesn't change a lot. It's pretty insensitive to change. Other questions? Sometimes, rather than using numerical models to characterize evaporation, physical models are used instead. And this is showing a pair of evaporation pans. And these are devices where you'll put in a certain amount of water into a pan whose characteristics have been very carefully studied, and they know, for example, the reflectivity of the pan, and based on the color of the metal and what it's made out of, how quickly water is going to evaporate out of that pan under certain conditions. And so if you are able to calibrate the pan to the crop that one is interested in, or you calibrate the pan to a watershed, what you can do is measure how much evaporation there was in the pan and then scale it up for the watershed. It might be that the pan evaporates water more quickly than a field of corn would. And so that a farmer who wants to know how much water has been lost by the corn crop, and therefore, if they're looking to estimate how much water has to be added by irrigation, they could keep track of what's happening to the pan. And the pan is also going to keep track of all of the factors that we've just been accounting for. You know, we said that evaporation rate is going to change depending on the temperature, depending on the radiation intensity, the atmospheric pressure, the wind, and all of those factors are naturally accounted for by the pan. If you think about the wind going over the surface of the pan and the profile of the wind at some elevation relative to the wave height inside of the pan and the humidity of the air. And so if you want to measure what's happened in the past, a pan can be very useful. Now, of course, this physical model won't allow you to predict what's going to happen under future conditions. You don't have the power of an equation. With an equation, we can say, well, what would happen if the temperature was 30 Celsius and the relative humidity was 20% and blah, blah, blah. You can come up with any combination of variables you want to understand, but the pan has to actually be in those conditions. And so we use the physical model versus the numerical model under different conditions. And the pan can be inside of a reservoir if you want to measure the evaporation of a lake. This little floating pontoon here is meant to quantify the evaporation of the reservoir itself. You're just measuring the water levels change in the pan. And it looks like they also have the wind speed is being monitored, and there's probably an antenna on there to transmit the data. Looks like a solar panel to keep it powered. When one knows what's happening to a pan, to the evaporation in a pan, then there are reference tables that would then relate the performance of a pan to a certain crop. And this is just showing you that if you have a pan that's surrounded by a green crop, then what percent humidity is going to allow you to relate the pan's performance to the crop performance. And so these values here are K sub P values. And so if you observed a certain amount of evaporation from the pan, let's say you observed 10 centimeters of evaporation from the pan, then you'd want to know what happened to my short green crop. Well, if the humidity is between 40 and 70% and you've got this pan 10 meters upwind of the crop, then you'd select 0.7 as the conversion factor. So you'd multiply the observed pan evaporation of 10 centimeters by that factor 0.7, and then you'd say probably there was 7 millimeters of evaporation from the crop itself. In every case, you can see that it's less than 1. So there won't be more evaporation from the crop than there was from the pan. But if you're further upwind, then the relationship between the pan and the crop is closer together. 0.85 is closer than 0.65. And you can also see that as you have high humidity, then the pan and the crop will have similar performance. So when we get together in class next time, we'll work through this evaporation example, and we'll also take a look at one other method for estimating evaporation that's on the homework. But what I'd encourage you to do is go ahead and download that data from the homework assignment. Start doing the parts where you have to download. I think there's two websites you need to visit to gather the data for the homework assignment.